Hello everyone. So last time we saw that support vector classifiers cannot actually give us a good decision boundary when the classes are not linearly separable. In fact, we ended our lecture with an example where the classes were separable but not linearly separable. Okay. So to handle such situations, we have to do something else. We have to come up with a better version of this classifier, and that's what support vector machines would do for us. Okay. So one option is when we want to go from linear to non-linear, what we do in regression, the easiest thing that we can do is we go for polynomial regression. Okay. So we, instead of having just y equal to beta naught plus beta 1 x plus epsilon as my model, we go for y equal to beta naught plus beta 1 x plus beta 2 x square plus beta p x raised to p plus epsilon as our model. Okay. So one option is, let us do something like in support vector classifier. So what do we mean by that? So instead of just having x1, x2, xp as my regressors, let me introduce x1, x2, xp and then x1 square, x2 square up to xp square. So our objective function would have different conditions. So now we would try to again maximize the margin. So maximize m over many parameters. Let me first list down the conditions, then it would be evident which parameters we have to see. So subject to yi into beta naught plus, now we have to accommodate both the original terms as well as the square terms. So summation beta j1 xij, j going from 1 to p. Okay, this is for original terms, and beta j2 xij square, j going from 1 to p. Okay, so this is for square terms, and this should be greater than or equal to m into 1 minus epsilon I, and of course the other conditions still remain. So summation epsilon I should be less than or equal to c, epsilon I is greater than or equal to 0, and now we have to worry about these betas as well as these betas. So double sum beta jk square should be 1, where k goes from 1 to 2 and j goes from 1 to p. Okay, beta j1 is for a linear term and beta j2 is for corresponding quadratic term. Okay, so we are going to maximize over all these betas and of course epsilons and m. So beta naught, beta I1, beta 11, beta 12 up to beta P1, beta P2. Okay, so 1 1 1 2 2 1 2 2 3 1 3 2, we have all those betas. Okay, and of course epsilons, epsilon 1, epsilon 2, epsilon n. So what we have done is we have just actually we are again using support vector classifier, but now we are bringing in square terms. So we can say this is support vector classifier in a higher dimension. Okay, so in some dimension it is still linear. So if I consider x1, x2, xp, x1 square, x2 square, xp square as my regressors, with this dimension it is still linear. However, in our original p-dimensional setup, it now becomes non-linear because of the square terms. So this is a good way of extending. But the problem is it doesn't stop here. I might want to include interaction terms like x1, x2, x1, x3, something like that. I might want to include cubic terms. I might want to include, say, logarithms, exponentials. So the problem becomes intractable pretty soon, because what all things are you going to try? And if you have so many things, does it still remain, can you still get an explicit solution? So people thought there should be some alternative to this, some easier way of handling this. Okay. So what they thought was, let us try to see what the original solution looks like. Now we didn't actually solve the support vector optimization problem, but the solution can actually be represented in this way. So the classifier, linear support vector classifier, can be written as beta naught plus sum over alpha I x xi I going from 1 to n, where x xi is inner product. Okay, so it is inner product of whichever x. So you want to see what is the value at x, so you take inner product of that x with every xi. Okay, this is actually the solution for the original support vector classifier optimization problem. So the solution is in terms of inner products. I think you can see it is slightly similar to what happens in regression. We get covariance of xy, so it's kind of like that. Okay, now in fact there is one more interesting thing. Not all alphas are 0. So alpha is non-zero only if xi is a support vector. And we know this, that the final equation depends only on the support vectors. It doesn't depend on others. So in fact my equation gets further simplified. It is fx equal to beta naught plus alpha I inner product of x with xi when I belongs to the set of support vectors. Okay, so S is set of all support vectors, indices for support vectors. So is there any way in which we can generalize this? That's what people started thinking. So instead of having simply inner product, can we do something else? So they introduced what is known as a kernel function. Okay, so a kernel function is considered as a generalization of inner product. So linear kernel would mean simply usual inner product. Okay, linear kernel is simply your usual inner product. However, we can have a polynomial kernel. Okay, so we can have a polynomial kernel of degree d. So if I want to write, so instead of taking inner product of two observations, if I want to take polynomial kernel over two observations, so say ith observation and jth observation, then this becomes 1 plus sum over k going from 1 to p, because each of them is p dimensional vector, right? Every observation is a p dimensional vector. So maybe we want to write this. So k going from 1 to p, xik xjk whole raised to d. So this part is still like the inner product. Inner product is dot product. So this part is still like the inner product. But now we are taking dth power of that, and this kind of works like intercept thing. Okay. So we are taking the polynomial kernel of degree d. And if we now say that my solution would look like fx equal to beta naught plus sum over alpha I k x xi, where I belongs to support vectors, and now I try to solve for beta naught and then all these alpha i's, then I get a non-linear decision boundary. Okay, polynomial decision boundary. So this is one example of a support vector machine. Of course, this is one specific kernel function. We can have some other kernel function. One other widely used kernel is known as radial kernel function. So what is radial kernel? K xi xj for a radial kernel would be e raised to minus gamma sum over k going from 1 to p xik minus xjk whole square. Does this term look familiar? This is basically square of Euclidean distance between ith and jth observation. Okay, and I am having e raised to minus gamma times that distance. So if this distance is high, then I have e raised to minus very large number. So basically this becomes almost 0. If this distance is low, then this quantity becomes high. What do I mean by that? So suppose a particular observation, say let me say first observation is far away from x, then kx(x1) would be almost close to 0 because the distance is high. As a result, in fx, kx(x1) would have this alpha 1 would have very low contribution. Okay, so what does it mean? That in radial kernel, what happens is the observations which are close to the point at which we are trying to evaluate, they play a larger role, whereas the observations which are far away, they have very less role. So radial kernel is essentially very local in nature. Okay, so nearby observations get a lot of importance, whereas the observations which are far away get less importance. And as a result, you might be able to capture even smaller patterns. Okay, so we saw this example, like you have one class here and you have some other class here. So things like that can be separated by radial kernel. Okay, so such patterns can be captured by radial kernel. So polynomial kernel, radial kernel are some of the examples of how support vector classifiers can be generated to, can be extended to support vector machines. Okay. As I said, the necessity of introducing kernel comes from the fact that if you just want to extend the parameter space, there are just too many parameters. Okay, it becomes difficult, and it becomes mathematically it becomes very difficult to solve such an optimization problem. Okay, so now that we have already incorporated nonlinear things, support vector machines become pretty good classifiers. In fact, in many real life applications, they give good results even when the class boundaries are pretty complicated. Okay. But in all this discussion, you might have realized that we are talking about two classes only. We started with -1 plus 1 as two classes, and that's how we defined the optimization problem. Okay, so how do you generalize it to multiple classes? Because yes, there are going to be scenarios when we need multiple classes. So how to do that? Now there are two ways of handling multiple classes. One is 1 versus all, and the other is 1 versus 1. What do I mean by this? Suppose I have three classes. Let me call them class 1, class 2, class 3. So what I can do is, maybe I can build choose two classifiers. 3 is number of classes. So class 1 versus class 2, I built one support vector machine. Then class 1 versus class 3, I build another. And class 2 versus class 3, I build another. And in every classifier, each of these classifiers, I see where my observation ends up. And then I take mode of the final classification. So suppose here it ends up in C1, here it ends up in C1, here it ends up in C3. Then I say that okay, twice it is going to C1, so let me put it in class C1. Okay, so this is 1 versus 1 approach, where we take all possible pairs between classes, do classification, and then record where the observation is landing, and then finally we take mode over all such classes. Okay. On the other hand, in 1 versus all, what we do is, so we put C1 versus C2, C3 are considered as one class. Then we put C2 versus C1, C3 as another class. And then we put C3 versus C1, C2 as one class. So 1 versus everything else. And here we can kind of order where it is, the probability of it going to C1, C2 and C3. So wherever it is largest, we put it in that class. Okay. So we can say, if for example here the prediction is C1, here the prediction is this, and here the prediction is C3, then between C1 and C3 we have to see which prediction is more, we can be more confident about which prediction. So the margin is high in which prediction, and suppose it is in C1, then I'll say okay, put the thing in C1. Okay, so this is how we can handle multiple classes in support vector machines, from binary to multi-class. So I think you have now got a clear idea about what is maximal margin classifier, how it gets generalized to support vector classifier, and then how it gets further generalized to support vector machines. Okay, so let me stop here. Thank you.